Sehr geehrte Frau Rektorin, liebe Kolleginnen und Kollegen, liebe Studierende, meine Damen und Herren. Ich freue mich, Ihnen heute einen neuen Kollegen in unserem Departement vorstellen zu dürfen, Emmanuel Kowalski. Er wurde 1969 in Grenoble geboren. Seine Vorfahren kamen, wie der Name verrät, aus Polen. Und eine genetische Prise Abenteuerlust hat ihn vielleicht dazu bewogen, nach dem Grundstudium an der École Normale Supérieure in Lyon die Doktorarbeit nicht in Paris zu schreiben, sondern an der Rutgers University in New Jersey. Nach einer Stelle nachher als Instructor an der Princeton University und dem Institute for Advanced Study am gleichen Ort hat er eine Professur an der Université de Bordeaux angenommen und wurde danach an die ETH gewählt, wo er seit dem 1. Januar dieses Jahres ordentlicher Professor für Mathematik ist. Emmanuel Kowalski versteht inzwischen schon recht gut Deutsch, wie er mir gesagt hat. Ja. Aber seine heutige Einführungsvorlesung wird er auf Englisch halten und ich wechsle jetzt deshalb die Sprache. The area of Emmanuel Kowalski within mathematics is number theory. In particular, the analytic theory of L functions. Although number theory is one of the oldest areas, it is by no means exhausted. For instance, the theory of L functions, which he studies, has played a key role in the recent proof of Fermat's theorem by Andrew Wiles, which received a great amount of public attention. And also number theory is generally classified as pure mathematics. It has many applications in cryptography, computer science, and physics. Moreover, Emmanuel Kowalski's research has interactions with many other areas of mathematics, like algebraic geometry, group theory, or probability theory. He has already started to contribute to the mathematical life in Zurich, and we are very happy to have him in our department. His publication list has more than 30 entries, including 3 books. One of them, jointly with his PhD supervisor, has the monumental length of 615 pages, and it's already a standard reference. Emmanuel apparently likes to write, and he writes well, as one can see also from his blog with the title Comments on Mathematics Mostly. The title of today's lecture is The Art of Sieving. Most people presumably know that mathematics shares many aspects with art. Mathematicians are often not satisfied with a correct proof, they aim for a beautiful proof. But the non-specialists today that are present wonder presumably what a down-to-earth and maybe a bit dull thing like sieving has to do with mathematics and art, and we look forward to learn about the connection.
Thank you for the very kind introduction, and I hope that the lecture will explain a little bit about what is sieving and why it can be considered to be just not science, but also a bit of art. So people might wonder, what is this background picture doing? It's actually an animal from Zurich, because it's a picture I took in the Zurich Zoo in the rainforest area. And I like it because it kind of, it's an animal that changes colors and changes shapes, presumably. And prime numbers also tend to change shape depending on the way you look at them. And they are very hard to catch, like a chameleon would be if he was not so slow. Okay, so I will start, and I think I will switch to the version of the lecture which does not have this background, because it makes the text a little bit hard to read. Okay, so I will speak about sieving in general and why it's interesting. But first, I want to introduce the main objects, historically at least, that were the subject of Sieve. they are the prime numbers, which are often referred to as being the elementary particles of mathematics. And the reason this is not a bad analogy is that they are the natural numbers, so I call them usually P, which cannot be split as the product of smaller numbers. It's something that's fairly natural to consider, because if you have a big number, you might want to write it as a product of smaller ones. So here are examples of prime numbers. The last one is actually the largest one known today. So 2 to the power, 43,112,609 minus 1. So which means you take 2 and you repeat it these 43 million times, and you take the product of these numbers, and then you subtract 1. So this was discovered actually just, it was proved that this is a prime number only in August this year. Examples of numbers which are not primes are here. So this means, for instance, that the date of today, 8/10/2008, is 8 times this other number, and it's not obvious, but it's actually true that this other number is a prime number. Okay. And as I mentioned, this largest known prime number was found only recently, and I guess there's a U missing in the text. Okay. So when you have prime numbers, one very important thing you can do is study factorizations of arbitrary numbers. And this may sound like something that's not particularly interesting, but I will try to explain why this is actually very important even in real life today. So if you take a number, either it's prime, or if it's not prime by definition, that means you can split it in 2 smaller pieces. And then you repeat with each factor, and at some point you have to reach the number 1. And this gives you a factorization. So here is, for instance, a number I picked up more or less at random, and 1 sees the prime factors. So 5 appears twice, so it's 5 times 5 times 7 times 7 times 53 times 107. And the last one, it's not clear, but it's also prime. And it's a very important fact is that if the prime factors which occur are ordered, then they are unique. You cannot have 2 different ways of doing this decomposition. And this is not completely obvious, but it's not so hard to prove. And also the number of repetitions are fixed. Okay. So now I'm going to give 3 reasons why people might be interested in prime numbers, which are essentially in reverse chronological order, and probably in reverse order of interest to people who really are not interested in mathematics. So the first one I think will convince everyone that there are lots of real-life interest in studying prime numbers, but it's the last one historically, and it's related to what was mentioned about the links with cryptography in some sense. Okay, so one reason primes are interesting is because they interact with factorization in the following way. So it's fairly easy to find prime numbers and to check that a number is prime. So here I just took 2 numbers, which I will explain a bit later on. They're not taken at random. And as you can see in this computer printout, it took 137 milliseconds to check that they were prime. 137 for the first one, 36 for the second one. So this is very, very fast. On the other hand, if I take the product of those 2 numbers, but I don't tell the computer that I constructed this product in this way, and I ask him to find the 2 numbers, then it's very, very difficult. So in this case, I stopped the computer after 1 hour and 53 minutes. I could have let it go for much, much, and much longer, because this is actually a historical example. This was a challenge put up by a company interested in computer security. And so it took 30 years of non-stop computation, or the equivalent of this on many machines, in 2005 to do this computation. Okay. And if nowadays any of you or anyone was able to do this type of computation, let's say in 3 weeks, I think that many governments and many companies would be very interested in talking with you. And here is the reason. So this type of fact is the basis of computer security nowadays. And other problems like this also occur, but it's really the basic idea. So let's give an example that's a little bit contrived, but should be a bit convincing. So suppose you have a spy agency, and they want to send a secret agent to a hostile country, and this secret agent has to meet a contact somewhere in this hostile country. Now, of course, it's not clear for the secret agent B that the person that comes to the appointment is really the contact. And the contact also might not be sure that the person coming is really the secret agent and not someone trying to catch him or her. Okay, so here's a way you can do this with prime numbers. So if you give the number P1, P2 to B, so the number P1, P2 was this huge number, which I didn't write down, but that was very, very hard to factor. So you just give this number without telling him or her what are the two factors P1 and P2. On the other hand, to the contact, you can transmit only the number P1, so one of the two factors. Now, when the people meet, so B and C meet, and then B can give N, so the product P1 times P2 to C, and immediately C can convince B that he or she is the right person by just giving P1, because she knows P1 as the agency gave it to her, and knowing P1 times P2, she can give P2 by just dividing. N divided by P1 is P2, and this is also very, very fast to do. And the fact that this computation comes right will immediately convince B that C cannot be an imposter. Because as we saw earlier, unless the meeting happens 30 years after the prime numbers were given, at the current time, we don't know a way of doing this faster. Okay. So this is a reason that I think that clearly it's contrived, but similar problems and similar constructions are used in more regular security in credit cards and so on. Okay. So this was the first answer, but this type of security and security concerns only exist since about maybe 40 years at most, because we need computers to be able to do this type of computations. So another answer that's a little bit earlier on corresponds to a scientific way of why primes, scientific reason why primes are interesting, is that they are very fascinating by the combination of deterministic behavior and complete randomness coming from this deterministic behavior. So nowadays it's common to term this as a dichotomy between structure and randomness. That's two key terms which are being used more and more in the literature. And we'll see another example of this later on. Okay. And why does the randomness come from? The randomness comes from the link, the fact that you can take numbers and you can not only multiply them, which with prime numbers is fairly easy, but you can also add them together, and then you get bizarre things, because the way a number can be expressed as product of primes changes a lot, and in a way that seems completely chaotic when you add other numbers. So here is a very simple example. So if we multiply 30 times 2, that's 2 to the power 30, which is obviously not a prime number, and has 30 different prime factors. As soon as you add 1, then we find that there's 6 factors, one of which is repeated twice. We add 2, and then we have 4 factors, and none of them is repeated, and one of them is much, much larger than the others. We add 3, and we have another prime number. We add 4, and then we have 3 factors, including one that's repeated, and then another that seems random. That's a big one, and so on. Okay. So prime numbers are determined in a completely deterministic way, because the definition doesn't leave anything to do with randomness. And the structure comes from the fact that when seen from far away at least, they look very reasonably well distributed. So here is a graph which shows the number of primes up to x until about 10 million. So it looks actually a little bit like a line, a straight line. It's not quite a straight line. But here, I didn't draw a straight line. I really just plotted the various points, and it just happens that the various points meet on a very, very regular curve. Okay. Now, when we look a little bit more closely, the primes start behaving in a very chaotic way and in a very random way. And in fact, so I'm going to illustrate that it seems that any interesting probability distribution, so what does it mean? It means that any interesting probabilistic phenomenon, any phenomenon that seems to depend on random behavior seems to be also be something you can find within the prime numbers when you look closely enough. And I'll give a few examples of this. So the first one is the normal Gaussian distribution. So this is what you get when you have a very chaotic, purely random walk, as I illustrate on the graph on the left. So where you start from the origin and for a length of time which is fixed, which can be normalized to be 1, you just go up or down completely randomly, and you look at where you arrive at the end. So this type of graphs happens a lot in physics, in biology, because the name Brown refers to a botanist who observed this type of behavior in movements of pollens, particles inside pollens in the 19th century. And it occurs also, it was supposed to occur in the stock market. And I guess from some parts of it look convincing enough today. And so if you look at where you end up after the given length of time, so time 1, and you look at what is the likelihood that you get closer or not to the origin, you get a curve which is like this well-known bell curve. So the fact that the point 0 is the highest on the curve means that it's the most likely probability is that you're going to be close to the origin, close to 0 after this walk, and you cannot be very, very far away from 0, except with very, very low probability. So this is a type of distribution which occurs in nature all the time. Many, many behaviors are modeled by this type of distribution. So as I said, you can find it within the prime numbers. So it's a theorem due to Erdős and Kacs. So it looks a little bit technical, but let me explain what it means. So you take a very, very large integer, and then you look at how many prime numbers will divide it. So that means you do this process of cutting it in smaller and smaller numbers, and you count how many factors occurred. And then you normalize it by subtracting what is log n. So log n you can interpret as being simply you take the number, it's very, very large. You take the number of digits of the number. So if you have, let's say, 10 to the power 100, this number of digits is 100. And then you take again the number of digits of this. So this will then take you this 10 to the power 100 becomes 100 and then becomes 2. So it's very, very small number, usually. And you divide by the square root of this. So the square root of a number is about, you take the number and you cut out half of the digits. That tells you more or less what's going to happen. Okay. And it turns out that if you take many numbers of very large size and you put on a graph what is the value of this expression, then you will get a curve that's exactly shaped in the same way. So most of the time, this will be close to 0, meaning that the number of primes is close to log n, and so on. And it's an actual fact that can be checked numerically, but the fit is not very good, actually. I didn't put a graph of the experimental data because it's not very good. You need really huge numbers for this expression to look convincing. But it's something that has been proved to be true. So it's actually one instance where something that is true is not easy to check numerically, and later on we'll see examples where the check numerically is astoundingly good, but we don't know at all how to make the proof. Okay. So the second example I wanted to give is probably the second most important distribution, which is the Poisson distribution. So it can be explained in very many different ways. So again, I took an example from physics. So if you have a given substance which is radioactive, and you look in a given length of time how many disintegrations within it are going to occur, and you plot, let's say, how many times one disintegration occurred in 1 second, how many times 2 disintegrations, and so on, and you will get a graph that's a little bit like this one. So for instance, here the most likely outcome is 4, which means that on average you have 4 disintegrations, let's say, per second. But sometimes you have only 3, and 3 is just a little bit less likely. Sometimes you have only 2, and it's a little bit less likely. Sometimes you have 0, sometimes you have 1. And much more than 4 is very, very unlikely. And this is also used to model, for instance, the length of waiting lines in supermarkets and things like this. So it's a really frequent distribution. Apparently, I think the first theoretical study of it was the number of deaths by horse kicks in the Prussian cavalry, which is something that happens once in a while, but not very often. This is what I heard. I don't know if it's true. Okay, so now here's an example where supposedly this distribution is going to arise within prime numbers. I said supposedly because we don't know how to prove this. There are good arguments that show that, and the numerical evidence is pretty good, but it's not proved. So the way to do this is, let's say here I said the most likely value was 4, so let's take c equals to 4, and you look at how many primes there are between a number x and this number where you add 4 times this number of digits, more or less. So x and x plus c times log x. So for instance, if x is 10 to the power 100, you will look between 10 to the power 100 and 10 to the power 100 plus 400, something like this. So you're going to get a small number of prime numbers. Sometimes there will be 0 of them, sometimes there will be 1, sometimes there will be 2, sometimes there will be 3, and you can try and look at which is the most likely to be. And it turns out that we hope that it's going to be exactly the same as the Poisson approximation. So here I drew a graph, and I don't exactly remember what was the value. It was probably 10 million with c equal to 4. And you can see the graph is not entirely dissimilar to the one above, but it's not very similar either. So you could, nobody would bet that the first one is the right one just based on the second graph, I think. But there are also interesting heuristic arguments that suggest that this should be correct. Okay. Now here's a much more fancy type of distribution, which I will go pretty quickly on. So there's a very kind of complicated density, which has to do with when you look at supposedly it's also in physics, I think it's not entirely established, but you look at a very large nucleus with many, many protons and neutrons, and it has a certain number of energy levels. It has infinitely many energy levels. And you look at how they are spaced, which is something that's of high interest to physicists, although I don't know much about it. And it turns out that the spacings tend to obey a certain probability law. They are not randomly spaced. They should behave in a way that's similar to a probability distribution. Okay. And it turns out that you can find it also within the prime. So I don't explain what is the Riemann zeta function, but it's just to give this graph, which is really amazing. So the graph, it's hard to see, but there's actually 2 things on it. There's a continuous line, and there are small circle dots, which you can a little bit see on the very left towards the origin. So the continuous line is supposed to be a theoretical prediction, which is this GUE distribution, which I'm not explaining. And the small circles are supposed to be, and there are numerical data from this Riemann zeta function, which is connected with prime numbers. And here, I think that, at least for a physicist, this is a proof. It's not possible that this thing is wrong when the fit is as good as that. And here, it's even worse than the previous example with the Poisson distribution. The numerical evidence is even more convincing, but we have even less of a clue of how to try and actually transform this into a real proof. There's no connection that is known between these 2 very different things, this GUE thing and this Riemann zeta function. So here, as I said, this is the most recent numerical work on this, which were done by Xavier Gourdon in France. So I took the picture from his paper. And now here is the maybe most convincing reason why primes are interesting for, at least for many of us, which is just they're interesting because they're interesting to humans. And they're interesting to humans simply because humans are experimentally interested in them. It's just a fact of life. Since the very beginning of mathematics, there have been people, maybe not so many of them, not certainly everyone, but many people have been completely fascinated by prime numbers. And these people have been of all kinds. So there are people who really are what one can call amateurs, so people who are interested in them without being professionals who make a life of studying prime numbers. So here is one example of an amateur which is fairly well known in this field. So Christian Goldbach, I think was the first name, who was the first to suggest that if you take any integer which is even, you could find 2 primes such that the sum of the two is this number. So it's a kind of a strange question, and it's a question that many people actually have dismissed as being uninteresting, because when you have prime numbers, you should not add them. You should just multiply them. But this is something that seems to be true. We don't know how to prove it, but it seems to be true. And so it was posed by someone who was really an amateur in this sense. Here's a very similar and looking question. I don't know what the A stands for, but maybe Alphonse, let's say. Alphonse de Polignac. In the mid-19th century, so he said the following. I think he was the first to suggest that you could find infinitely many primes such that p plus 2 is also a prime. So it's not possible that p plus 1 is a prime, because usually a prime number is odd, and so p plus 1 is divisible by 2. If you take 37, plus 1 is 38, which is 2 times 19. But p and p plus 2, there doesn't seem any reason why they shouldn't be prime. And for instance, 11 and 13 are both prime numbers, and numerically speaking, you can find many of them. And so we expect that there are infinitely many. We don't know how to prove it. So those were two important conjectures that people are certainly still very interested in, and which they don't know, and we don't know, no one knows how to prove it. Although, I mean, if you look on the web, for instance, you will find 5 or 6, maybe 10 different proofs between quotes of these facts, but usually they don't stand up to examination. Okay, so those are the amateurs, but also one way to see that primes are interesting is to compare what people interested in primes have done in other fields. And you can see that some of the really most renowned scientists of all times have been really fascinated by primes. So I try to think of what is a convincing way to convince people that those people are really renowned. And one way is to say that, well, someone who's renowned, maybe there will be a stamp that will be produced with him on the stamp. And it turns out that the 4 examples I was thinking of were people who have had stamps made for them. So the first one is Euclid, so who's known as the founder of geometry, of at least axiomatic geometry, and he's also the first one to have proved that there exist infinitely many primes. Okay, the stamp here I think comes from an obscure country, I don't remember which one. It seems that Greece hasn't produced a stamp with Euclid, which is surprising, but seems to be true. But it does have a stamp, so it's the Maldives, yeah. Okay, now another scientist that some people would consider as an amateur, but made so many important contributions to optics, probability, and so on that it's not fair to call him an amateur like the other two were before. So Pierre de Fermat, who had the stamp made after the proof of Fermat's last theorem by Andrew Wiles. And he was also fascinated by prime numbers, and I will select one of his affirmations, which is interesting. He says that if you take any integer positive, so 1, 2, 3, 4, 5, and so on, then you could always construct a prime number by multiplying 2 that many times. That will give you a huge number. And then redoing this, multiplying 2 that many times again, and then adding 1. So that was a kind of bold guess, because no one has ever been able to produce a formula giving only primes, which is reasonable. And it works for n equals 1, 2, 3, and 4, which at that time was not so bad evidence, because the next one is pretty big, but the next one doesn't work. So Leonhard Euler, and here I had a choice of many stamps. So actually there was one last year for his 300th anniversary from Switzerland. But I found that the old stamp from 57 was nicer, so I took this one. And so he proved that 2 to the power 32 plus 1, which is 2 to the power 2 to the power 5 plus 1, is not prime. So this shows that also these scientists could also make mistakes. And Euler, of course, made so many contributions that it's impossible to list them all. I think his collected works are not yet even completely published in full. There are so many things in all the fields of science. And certainly not only in the study of prime numbers. And the last example is Carl Friedrich Gauss, who is also one of the most renowned scientists ever, who also contributed in essentially all fields. And so the observation on the right was something he did when he was a teenager, and it was the first time that someone seemed to have guessed in what way primes have structure. as I mentioned earlier, this curve which looks very regular, which of course people couldn't produce so easily at that time. But there are tables going fairly far away. And from this table, he stated that if you have a very large integer, so how should you bet that this is going to be a prime number? What would be a fair bet against someone that the number is going to be prime or not? And the fair chance is 1 in about log n, so the same log n that occurred before. And so precisely log n you have to think as being 3 times the number of digits. So that was Gauss' prediction. As we'll see later on, it's actually correct. Okay. Now, actually, I realized that I haven't started speaking of the Sieve yet, so it's time to go into that. So what we do with Sieve, we try to count prime numbers, essentially. So we see that prime numbers are interesting, and so we try to count them. And this has many applications. So the name comes from the sieve of Eratosthenes, and it's devised to produce lists of prime numbers. So here I give the examples of how this works. So you start with a list of numbers from which you want to select the primes. And the first number which is not marked, so like in this case it's 2, you say it's a prime because it's not been excluded. Then once you know that 2 is a prime, that all numbers which are multiples of 2, so 1 in 2 is not going to be a prime. So in this case, 4, 6, 8, and so on. And so you cross them, or in this case, I just put them in a darker color. Then you continue with the first number which is not crossed, in that case 3, because it was not colored in blue, and I took red as a color for 3, and you put in all the multiples of 3. So here you may say there's some multiples of 3 which are missing, and it's actually theoretically important that, in fact, 6 is a multiple of 3. It's 2 times 3, but it was already in blue. So in a way, it was not necessary to exclude it, because it was already excluded. But still, it's important for later on to remember that we crossed 6 2 times. And so I added the colors, and you get that 6 is this kind of dark violet from this one. And then you continue with 5. So 5 is green, and you remove all the multiples of 5. And then you have to be careful with the multiples of 5, which are also multiples of 2 or 3. And then you do this with 7 and so on. So here it's easy to see that the list is complete up to 60, and the numbers which are prime are those which remain. So in that case, so those which were selected 2, 3, 5, and 7, but also all those which have remained in white, which have never been crossed, up to 60, so you get these prime numbers. And this is something that's actually doable in practice if you have a list of numbers, because the crossing is done regularly. So it's 2 by 2, and then 3 by 3, and then 4 by 4, and 6, and so on. So it certainly is much faster than trying to factor every number. Okay, now let's try and generalize this to describe what should be a general type of sieve. So we start with a set of interest, which I call X, so it could be the integers. And then we construct a subset by removing those which satisfy any of a certain set of conditions. Let's say here I have K conditions. And the principle of the sieve is that, so suppose there's some probability that the ith condition holds. So you should be in the set C1 with probability delta 1, in C2 with probability delta 2. So maybe there's 1 chance in 2 in being in C1, 1 in 3 in being C3, and so on. Then if those conditions are almost independent, which is just saying that if you know that C1 is true, you don't know anything about C2. If you know that C2 is true, you don't know anything about C3, and so on. Then there's a guess about the probability of Y, of being in the set Y obtained by removing all the conditions. And this probability should be 1 minus delta 1, which tells you what is your chance to not satisfy C1, times the chance of not satisfying C2, times the chance of not satisfying C3, and so on. And the second expression comes from expanding this product, and it's explained why this is sometimes called inclusion-exclusion. So you start with everything, then you remove all that seems to not work. But when you do this, you've crossed out twice certain things, which means that you haven't got the right answer. You have to add again, so that's the plus sign with the delta I, delta j. you have to add again what was excluded twice. But once you've done this, you've again made a mistake. You have to remove what was counted 3 times, and so on and so on. So there's plus and minus signs alternating. Okay, so this is just a guess. And in the first example, let's see how it works with prime numbers. So we start with the integers up to some bound, so 1 up to n. And the conditions are then the divisibility conditions. So condition C1 would be that n is a multiple of 2, n is even. Condition 2 would be that n is divisible by 3, so it's 3 times another number. And the probability of these conditions, it's intuitively, if you have a number, there's one chance in 2 that it's divisible by 2, because there's either odd or even with the same chance. Probability of being divisible by 3 is also not too hard to compute, and it's natural that it's 1 over 3, and so on and so on. And when you have divisibility by the case prime, you get a probability of 1 over this prime. Okay. So 1 over 10,007, for instance, should be the probability that a number is divisible by this prime number, 10,007. Okay. And then there's an observation, which is a bit technical, but it's important to make this thing work, is that if you have a number which is not divisible by such a prime number up to the square root of n, then it has to be a prime. So that means that if you take this set X, you remove all the numbers which satisfy any of the conditions where the number of conditions is governed by the size that the case prime must be of size about the square root of n. Then what will remain after this will be the white boxes in the example before. It will be the prime numbers essentially between square root of n and n. So let's say it's the prime numbers. Okay. So this is the Sieve description. And the guess that comes out for how many chance you should have to have a prime number of size about n, it should be this product. So the first term is 1/2, that's the probability of being odd. The second term is 2/3, it's the probability of not being divisible by 3, and so on and so on. And so the mathematical notation for this is product, so this capital pi means product of 1 over the inverse of the primes up to square root of n. Okay, so this is not a bad guess, but as we'll see, it's wrong, and it's another way, it's a second example of a situation where some scientists did not guess right. So it's wrong because if this is correct, then we know what this probability is. It should be 1 over log n, but multiplied by this constant 2 times c, where c is this constant which I wrote down. So this was proved by Mertens in 1874. And on the other hand, so the right number, so the number of primes, is about n divided by log n, which means the probability is about 1 over log n. Okay, so this was proved in 1896 by Adamar and Delavallee-Poussin. And so this confirms the intuition of Gauss, exactly. And shows that the intuitive description was wrong. Now, a second example is the twin prime. So what are twin primes? It's those numbers of Polignac, prime numbers p, such that p plus 2 is also prime. So we don't know how many there are, but you can also try and count them with Sieve. So this time you start with the same set, but the conditions to exclude that are that either n or n plus 2 is even, for instance, or n or n plus 2 is divisible by 3, and so on. And now the probability changes. So for the first one, it's still 1/2, because if n is even, then n plus 2 also, and if n is odd, then n plus 2 also. But for numbers divisible by 3, you could have a number which is itself divisible by 3, but n plus 2 is not. For instance, 3 is divisible by 3, but 3 plus 2 is 5, is not divisible by 3. So the condition in that case is not satisfied, despite the fact that n was divisible by 3. So the probability is larger. It's 2/3, and so on and so on. And for the case prime, you get 2 over this prime. So what is called the sifted set, so that's the set of the set Y that remains, the white boxes that would remain if you would do the analog of Eratosthenes construction with these definitions, would be the set of twin primes. And we would guess that the probability is given by this new expression, where I just replace the previous ones by the new probabilities. So 1 minus 1/2 is for even numbers, and so on. Okay. And as I said, we don't know if this is correct or not, but building on this type of ideas, there's a very strong conjecture which has been made, is that we can actually count, we should be able to count as precisely the twin primes as the primes, and there should be a little bit less of them. The probability should be about 1 over log n squared instead of 1 over log n. So it's a smaller probability. And there's this bizarre constant, which is one of the fun things in arithmetic, is that every once in a while you get to write these bizarre constants, and you can see what number that gives. And in this case, it's about 1.32. Okay, now I'm going to give some highlights of classical Sieve method, and then I'll be almost done. So one of the strongest results to date is already 70 years old. It's a result of Vinogradov, which says that we don't know about even numbers, but when we have an odd prime, at least, we know that we can split it as a sum of 3 primes. So the Goldbach conjecture says you start with an even one, and you should do with 2 factors only. So here we have an odd one, so we need at least 3 factors for parity reasons, and we can do it if it's sufficiently large, by which means something that's really, really larger than and a very big number. Then if we just want to look at twin primes, there's a very famous theorem of Chen, which says that, well, we cannot get a prime such that p plus 2 is prime, but we can get a prime such that p plus 2 is either a prime or a product of 2 primes. So it's as close as possible, in a sense, to being a prime number. So this result was also sufficiently striking at the time that China produced a stamp with it. So you can see on the top of the stamp there's the actual formula that Chen proved, which is more complicated, but corresponds to this statement. Okay, and a very strong result that was proved by my advisor and his colleague John Friedlander in '98. So that was just when I was finishing my PhD, and it was an exciting time to be around them at that time, because this was considered as a very striking result in the theory of prime numbers, a very new development. So what they prove is that you can find infinitely many pairs of integers x and y, such that if you take x squared plus y fourths, you get a prime number. So it might seem strange to look at this type of expression, but again, we're mixing addition and multiplication, and we do this in a way where we still can control the prime numbers. And this is something which is always at the heart of Sieve methods, and for which any success is considered to be really nice. And I had actually prepared many more slides, but the time is over, so I'll just refer people to my web page, where I'll put the full set for everyone to look at starting tomorrow. All right.